Chapter 4 Control Volume Analysis Using Energy. So far we have considered closed systems. Mass was not allowed to cross the system boundary. In this chapter, we are going to consider open systems or control volumes. It allows mass to cross the system boundary. The fluid flow goes in and out of the system. We are going to introduce the mass balance and the first law of thermodynamics, or energy balance, on the open systems. These conservation laws are fundamental laws of nature. They apply to all processes. Also, we'll apply the mass and energy balance equations to steady operation devices such as turbines, compressors, nozzles, diffusers, and pumps. And lastly, we will take a look at transient analysis. Section 4.1 Conservation of Mass for a Control Volume. The control volumes or open system is a fixed region in space. So it is characterized by flowing fluid. So mass as well as heat and work can cross the system boundaries in open systems. So mass conservation law states that mass cannot be created or destroyed. In closed system, the mass in the systems remain constant as there is no mass across the system boundaries. In open systems, the mass in the systems may vary with time. Mass conservation may be expressed in mathematical form. M dot denotes the mass flow rate. It is the amount of mass flowing through a cross-section per unit time. The physical meaning of each term is described here. So dm subscript CV control volume over dt denotes time rate of change of mass contained within the control volume and time t. M dot subscript I, time rate of flow of mass in across inlet I at time t. M dot sub E, time rate of flow of mass out across exit E at time t. Consider a water heater. So cold fluid is going into the heater and hot fluid is going out of the heater. For example, let's say M dot I equals 3 kg per second and M dot exit is 2 kg per second. So according to the mass conservation law, 3 kg per second going in minus 2 kg per second going out of the system equals 1 kg per second. So 1 kg per second is the time rate of change of mass contained within the control volume in the water heater at time t. So the water heater accumulates mass at 1 kg per second. If the mass flow rate m dot is equal to m dot out, the mass of the system remains constant. The control volume may have several inlets and outlets, and the summation is used to evaluate the total mass transfer across the system. 4.2 Forms of the mass rate balance. So mass flow rate is equal to the density times area times velocity. The area is the cross-sectional area of the fluid, and the product of area and the velocity is the volume flow rate. It can be also expressed as the volume flow rate divided by the specific volume of the fluid. The reciprocal of density is the specific volume. The steady state indicates the properties do not change with time. A device may operate for a long time with the same conditions, and there may be no change in any properties of the system with time at a particular location. But the steady state does not mean the properties remain uniform across the system. They may vary from point to point in the system. For example, let's say this is a system and the temperature is a function of position. The temperature here may be 100 degrees Celsius, but temperature here may be 50 degrees Celsius. So the temperature varies from point to point, but temperature at the particular position doesn't change with time. This is steady state condition. So in these equations, the left term, time derivative goes to 0. Example 4.1. A feed water heater operating at steady state has 2 inlets and 1 exit. At inlet 1, water vapor enters at pressure 7 bar and temperature 200 degrees Celsius with a mass flow rate of 40 kg per second. At inlet 2, liquid water at pressure 7 bar, temperature 40 degrees Celsius entered through an area 25 square centimeter. Saturated liquid at 7 bar exit at 3 with a volumetric flow rate 0.06 cubic meter per second. Determine the mass flow rate at inlet 2 and the exit in kilogram per second and the velocity at inlet 2 in meter per second. So we have an open system, so mass going in from the inlet 1 and 2 and mass is leaving the system from exit 3. We are going to apply the mass balance to determine the unknown. Mass going in to the system from inlet 1 and inlet 2 and mass is leaving out of the system, and this is at steady state. So there's no change in mass within the system. All dm in the control volume over dt goes to 0. So m1 is already given, 40 kg per second. We need to determine the mass flow rate at inlet 2 and the exit and the velocity at inlet 2. First, let's take a look at the exit 3. So phase of the water is saturated liquid, which means quality is 0 and the pressure is given. So we know the two intensive and independent property. We can fix the state, and the mass flow rate is area times velocity divided by the specific heat. So volumetric flow rate is given 0.06 cubic meter per second, and we can determine the specific volumes at 3. See table A3. At 7 bar, specific volumes of the saturated liquid is here. So 1.1080 10 to the negative third cubic meter per kilogram. Let's calculate the mass flow rates at inlet 2, M2, M3 dot minus M1 dot. So both flow rates are known. And we need to determine the velocity at inlet 2. And the mass flow rate is volumetric flow rate divided by the specific volume. So we can solve it for the velocity at inlet 2. Mass flow rates and the area are known. We need to evaluate the specific volumes at inlet 2. At inlet 2, temperatures and pressures are known, so we can fix the state. And see table A2 is a saturated water table. At 40 degrees Celsius, the saturation pressure is 0.07 bar. But at inlet 2, the pressure is 7 bar, which is much greater than the saturation pressure. That indicates the phase of water is compressed liquid. We have a compressed liquid table for water, but we may not be able to find the correct tables at the given condition. So what we are going to do is to approximate the phase as saturated liquid. So at 40 degrees Celsius, specific volume is 1.0078 times 10 to the negative third. So the velocity at inlet 2 So all the unknowns were evaluated from the mass balance equations. 4.4 Conservation of energy for a control volume. The first law of thermodynamics states that energy cannot be created or destroyed. For closed system, the first law of thermodynamics can be written as delta E equals Q minus W. So E is the all forms of energy in the system, and Q is the heat transfer across the system boundary. W is the work across the system boundary. So it may be used for any closed system and in any process. The energy equations may be written in the rate form. So dE over dt equals Q dot minus W dot. So this is the energy balance equations for closed system. If there is mass transfer across the system boundary, the first law of thermodynamics will have additional terms. In open systems, mass flows across the system boundaries. And this is the physical meaning of energy balance for open system. And this is the additional terms related to the mass transfer. So mass carries energy. The energy carried by the mass consists of two parts. The expression in this blue box is the energy associated with the fluid. So the fluid contains energy in different forms, including the internal energy, kinetic energy, and potential energy. M dot, the mass flow rate at the inlet, mass flow rate at the exit. V is the velocity, Z is the elevation of the system. So these relations indicate rate of energy transfer into the control volume accompanying mass flow. This part indicates the rate of energy transfer out of the control volume accompanying mass flow. And the second part of the energy carried by mass is called flow work. So the flow work is the work required to push the fluid into the system or out of the system. So the fluid going into the system is pushed in by the fluid behind it. Or imagine a piston to push the fluid into the system. And this flow work corresponds to m dot I times Pi times Vi. In the same way, when the fluid is going out of the system, the fluid is pushed out of the system by the fluid behind it. And this kind of work is called the flow work. This flow work corresponds to m dot E Pe times Ve. And the flow work is expressed as P, pressure times specific volume. So we know that work can be expressed as the force times displacement. And the force in the flow work is the pressure times area. Area is the cross-sectional area of the fluid. So force times displacement. And area times displacement is volume. So work is pressure times volume. Therefore, flow work can be expressed as the pressure times specific volume of the fluid. So these terms in blue boxes are the energy carried by mass. The work for the open system has two parts, flow work and all other energy transfer by work such as electrical work and shaft work. And based on these two relations, we can write these equations. So internal energy, flow work, kinetic energy, and potential energy. So this is the energy of a flowing fluid of mass m. And for convenience, we combine the internal energy and flow work, and it's called enthalpy. So enthalpy is the sum of internal energy and flow work. This equation looks complicated, but it is often further simplified with appropriate assumptions. The change in kinetic energy or potential energy may be neglected, and the system may operate in steady state conditions. dE over dt may be 0. For multiple inlets and exits, we use summations to include total energy transfer across the system by mass. 4.5. Analyzing control volumes at steady state. At steady state, the properties do not change with time. So there is no change in mass of the system with time. This means that the mass flow rate going into the system equals mass flow rate going out of the system. So left hand side term dE over dt is 0 at steady state condition. For one inlet and one outlet system, this term indicates the change in enthalpy of a fluid, change in kinetic energy of the fluid, and change in potential energy of the fluid.